so that recorder's now on, is that I'll just give a little bit of a map. So the idea with integration, and I'll turn that down a little bit, is that as a map, you've got some basics. You've got up and under, and this is very definitely the know-how version. You've got the quotient, and they're always difficult. Anything with a quotient is always difficult. You've got the big one. You've got U substitution. Then you have a trig substitution, and somewhere there is the line that you draw around extension 1. So advanced kind of goes about there, and then we get into extension 1, and then we come to extension 2. So we've got partial fractions, and then we've got integration by parts. And I've noticed that DEs have gained a bit more of a profile in the curriculum, so I'm just going to add that on the back. So DEs, they used to be simple harmonic motion and some simple mechanics type problems, but they've actually started putting them in a bit more formally in the curriculum, I noticed. So mechanics, we'll call it. So there's a little bit of that going on. Now the other thing to remember is that there are two basic types. Now we've learned about a particular type. These are proper integrals. We've learned a little bit about improper integrals. So in the school system it's proper integrals, and basically they fall into the two categories of who can tell me what they're called? Two different types of integrals. It's a simple question, isn't it? You must want to punch me in the face sometimes. So definite integrals and indefinite integrals?
Yeah, definite and indefinite.
Yeah. So that's all it is. So indefinite, that's all it is. And often it's a big deal when you're introducing the topic, particularly if you're teaching it. And so these guys produce an expression which also has a plus C, and it's usually a capital C, and it's very picky. It's an error to leave that off. And this guy produces a number, a quantity, or an area. It's usually units squared. So those are very subtle definitions that pop up with these. So an example of this might be just integrate x squared dx, and so the indefinite version of that has no limits of integration. So it's up and under and plus c, so you get this expression. Okay, now I'll do some more after this week, but I won't harp on this tonight because I want to get back to eigenvectors and eigenvalues. But I just thought that it might be timely to put this in because it is coming up in our subject. For a definite integral, it'll ask for a number. So in a way, it's the same kind of thing, up and under, a very simple one. But it's now between 0 and 1. And I put in by the fundamental theorem of calculus, FTC. And so what that produces is this scaffolding. And students in schools tend not to want to do the scaffolding. They tend not to want to drop the 1 cubed over 3, the 0 cubed over 3. Now that's a polynomial, so the 0 doesn't count, but you can't do that for a trig. So this ends up being 1/3 units squared as a result. So they're two very different propositions. And I won't do the rest here, but I'll just basically do a quotient. So a quotient is basically the derivative of the function over the function itself is equal to the log of the function. Okay, so that's worthwhile doing some work on that in the coming few weeks, which I think we can do together. Okay, for me the most important one, as I said last week, is, and I won't do examples of these tonight, guys, I'll do them next week. Is that alright? I'm just kind of doing a map. A bit of a map. Now, U substitution for me is the most important thing. None of this other stuff takes if U substitution doesn't work. And in order to do U substitution, you need your chain rule to be robust. So if the thinking is let's do integration and the students falter, it may be because of the chain rule. The chain rule's not well processed by the time you get to integration. So in this particular example, it's usually in product form, but not always. So for example, if I have an x squared term multiplied by something like 3x plus 4, and that one there we might make a 3. So it has a higher power, dx. Now the recognition of the forms and how they work isn't always so obvious. Okay, so let me do it once this week, and then I won't do a definite integral. I'll just show you what I want to emphasize. Now, if we take the internal form and u is equal to 3x cubed plus 4, and then Leibniz notation, please, not just a dash, but an actual Leibniz notation. Okay, now the other thing that I didn't do was I didn't rush off like the chain rule and write something like that, incomplete. Okay, that's an error up front, because we do that with the chain rule. With the chain rule, we let u equal something and we dash off, and we straight away put it back in, right? So to show you what I mean, and straight away we could go y equals sine u. That's a very natural thing to do, because you're going to do your substitutions. So then you'll do your dy du and your du dx, and it makes perfect sense. You're going to chain those together. Dy dx, we're still going to have dy dx. Sorry to labour this, but it's very important. And then du dx. So dy du sine is cos, and that one's 2x. So when you put them together, you'll get 2x cos u, and u is x squared. And you can use technology to check anything that I do here. But this was a natural thing to do, to pop over here. And so that instinct, because you learn that with a passion, don't you? And you only just learn it, and then you start integration. And it's quite possible you start U substitutions. However, that habit is good for the chain rule, but it's not good for U substitutions. And unfortunately, it gets carried over. Students want to spend time on the integral, not the substitution. And I'll show you what I mean. By writing this out the long way, we'll get 9x squared. Okay, and then what we want to do is rearrange this. Now, I have too many students come to university and not know what to do next. Now listen, let me make this absolutely clear, and because I want you to remember it. Okay, it doesn't matter what you do. Your professional practice is your professional practice. So this is not me rousing or bellowing or anything. This is just me being an example of someone who emphasizes, and so when I'm emphasizing, it's for me. It's entirely your choice whether you follow this or not. You must understand that, right? So with this, so when I say please and I'm passionate, I'm imploring, or I'm begging. It's not a command or an instruction. It's simply, this is how this dude feels about this. Okay? It's entirely up to you how you translate that. Now, in this one here, so what I have is far too many students who can't see the picture here. And what we're actually looking for in the integration, which I feel doesn't get transmitted at school, is this. They're the actual substitutions. Now look, we wrote U. That's what we teach, isn't it? We teach U is the substitution. But it's actually these guys that we're looking to substitute out. And the arrangement of a simple thing like this is not well done. So multiplying both sides at least once, I would recommend doing this long way, at least once, so that students get into a good habit, okay? And dividing by 9, so we would have 1/9 du equals x squared dx. And any shortcuts you take, now this is again not a reproof, it's my opinion, because I've seen it not work when we get to heavier stuff. Any shortcuts are a waste of time in U substitution. Bad teacher. Now that's just rude, I know. But it's the temptation to teach shortcuts. It just saves so much time if you can just teach a shortcut. But they will come unstuck later. When they get in front of me at university, they will come unstuck. So here we've got the actual substitution. That's the game. This is the game. So all the competent ones who get this know this. So let's look. Is there an x squared up there? Tick. There it is. So we've got a substitution. Is there a dx? As mundane as that is, yes. So they're the two things that are actually going to disappear. So if we draw a line in the sand and write du and take the 1 on 9 out the front of the integration sign, that's the substitution of substance. As far as I'm concerned, when I'm teaching students, if they can't get to that point, we're kidding ourselves. Okay? The next bit, which is the thing that we would do with a chain rule. The next bit is we would put the u in, whatever form that was. Now I could have put a bracket there, I could have made that a square or 4 or what have you, but I'm just keeping it simple. Okay? So the integral then, that's the money one that we actually want. And so it's up and under. So it's going to become u squared over 2 times 1/9 plus c in this particular example. So u squared is 3x3 plus 4 all squared divided by 18 plus c. Okay, so for me, that's the technique, and that's just an indefinite one. So in coming weeks, we'll do. So please, I'm asking you, bring questions to these sessions on integration that you want me to do. Okay, and we'll classify them according to the map, and we'll go through them line by line like this. If you think that's valuable, let me know by bringing your, got this one out of this book, what's going on here, type questions. Okay, because this is it. This is for you. This is not how you teach the students. I couldn't care less. But in my opinion, you need to be able to do this for yourself. Okay. Now, again, using technology. Sorry to bring technology back into it. You can do an integration. I'll show you this, and it'll be on the video for you to scrub through. So you can do integration. And our question is, x squared 3x3 plus 4, x squared 3x3 plus 4 dx, and usually that's enough. And I'll show you how to do the multiple. Let's see what that looks like, just to see if we're in the right flavour. And it's x squared 3x3, okay, plus 4. And so we get, now that's been simplified. That answer's been simplified. So that often happens with the technology, that it gets simplified. Now, if you take I pay a minimal amount. I don't recommend. It's not my job to tell you what to buy, but I recommend getting a subscription. So my UTS thing is a subscription, and if you do that, you can get a step by step. Okay. Now, if you're sweating and you're on your own, and there's no one to help you, this is a great thing. Now, this is based. Wolfram Alpha is based on Mathematica, and that's what Mathematica I've based on my intelligent tutoring system. And so all of this unpacking is stuff that I'm very interested in terms of how we present to students for my own research. And so all of those things there. Now, sometimes it doesn't look familiar, and sometimes it looks exactly familiar. So, yeah, I encourage you to think about that. But it's, yeah. All right, so we can bring out factors and all the rest of it to simplify. All right, are there any questions or thoughts about that? Do you enjoy me? Sometimes I feel like I'm prattling on. Do you guys enjoy me doing this line by line stuff, or am I wasting my time? Are you happy for me to do it?
Yeah, I like watching the line by line stuff.
Yeah.
Yeah. So next week, do you want us to bring questions?
Oh, this is the time now. You've only got me now for 6 weeks. We've been doing the hard stuff.
Okay.
We're moving into a little bit of integration in the next couple of weeks. We've got a break, and then we've got DEs, which I really want to just throw open to you and show you how it all works, and systems of DEs. But backing all of that is this high school thing that you're engaged in. It's got to be relevant what we're doing, and I'm trying to cross the two things over for you, and I hope I've been effective in doing that in the last subject and this subject, in helping you to see that although the layers of the curriculum's a spiral curriculum, I don't know if I've ever explained that. So the maths curriculum's not linear, it's spiral. So what happens is you go across topics, and as you get across your years, what happens is you get, you know, you go through a particular topic and you get introduced to a new idea, and it gets harder and harder and all of that stuff. So all it means is that your spiral's up higher. So in that sense, yeah, I'm hoping that that's all right. All right, so I'm trying to pull them together for you to help make it reasonable. And, you know, I don't care what it is. I don't care what the source of it is. I don't care where you get it from. I don't care if it's stuff you're doing in your own math subjects now. Those staff can learn to love me because I help students no matter what. Okay, so that's the bit we're interested in. All right, so let's get back to eigenvectors and eigenvalues, if you don't mind. We can do that. Okay. Any questions? All right, now the trig substitutions are based around, that's why I passionately went through showing you that when you do the ddx of an inverse, like sine to the minus 1, that it ends up transforming into the integral. Okay, that process. Now, I don't know if that's clear. I'm hoping that statement that I just made is clear to you, but if you go back and unpack the ddx of sine to the minus 1x, you end up with a result that looks like this, and so the reverse process, they're linked very tightly. So that's why it's important to come to terms, if you're going to be teaching extension, to be able to unpack and we used implicit differentiation, didn't we, when I did those? So that's important. That's a biggie. Otherwise, you're just seeing a picture on a table and saying, oh, okay, if we integrate some form of an equation, what do you get? So if we integrate a form like that, what do you get? Oh, I see. We get sine to the minus 1. We get that kind of thing. I think we've got to be a bit more in depth in that. Okay, we've got to be better. And so that's why I've done that 4 or 5 times now. I've done this kind of thing 4 or 5 times so that we get this interchanging. Now, it's coming into the curriculum more and more that students are being asked to do integrations by looking at the ddx version and seeing that the ddx is the antiderivative. All right, partial fractions is not that terribly difficult, but there are some abstract type apparent rules that go into, why do we choose the forms of equations that we choose. And so that one can be a little bit tricky. I should maybe put that on the other side of integration by parts. But integration by parts also has some interesting things to it. So if you really want to be able to express your horsepower in mathematics, probably integration by parts is something you should be able to park on. And then over a couple of years, maybe 2 or 3 years, learn more about partial fractions. But of course, I've said to you all the way along to give yourselves time. All right? Don't beat yourselves up expecting you to be super dupers at the beginning. Give yourselves time. But certainly integration by parts is something that we could do. And we can have a look at DEs. I've done a couple of those simpler ones to talk about E and Lin and all the rest of it. All right, so we're going to go into the next part now, if that's okay. So that's enough of that. So please bring those. Call me out and say, come on, we're going to do a bit of integration first. And then we'll keep going with whatever we need to for eigenvectors and eigenvalues, and also our tute. But we're not having the tute formally this week. Okay. All right, so a typical question would be, now I'm doing it, do the whole thing complete so you've seen it. I like to do that, but then that's your kind of record of it, okay? So find eigenvalues. So we're going to do it kind of from first principles, and eigenvectors. And I'll just keep it simple. I'll do it 2 by at the moment of matrix A. And this will be posted, so you don't need to, put it there. So we've got AX. This is now the meta algebra, the matrix algebra, and also AX equals 7x. Right. So our matrix A is 1, 6, 5, 2, and our column vector is x1 and x2. Now that could be any sets of variables that you want, and often they change to match. So if I then do the augmentation and think about expressing this in this form, the way I'll put them together is this matrix algebra. So in the first instance I'll have 1, 6, 5, 2, and then I'll multiply that by x1 and x2, so that satisfies this pair over here, and I'll say that that's equal to some scalar called lambda, which is just a number, multiplied by x1, x2, and that satisfies the right hand side. So I've put it in this form. So this is like the big starting point. Alright, now with most algebra, you're used to using operations to move these guys around, and so that's what we'll be doing. We'll be moving these guys around simply by using matrix algebra. So if we're going to use lambda x over to the left hand side, we do minus lambda x. We go minus lambda x. What you do to one side, you do to the other, and so you get ax lambda x equals 0. So that's typically what you interpret that. So if I do that here, I'll end up with there's a lot of repeating of matrix writing when you do it, so you'll just have to forgive me for that. Minus now what was on the right hand side is equal to 0. So that's the next big step. Alright, now we insert a couple of ideas just to be completely annoying, because we can, to help it make sense. And I'll show you the jumping point. I think I mentioned that last week, but we're pre the jumping point at the moment. Now if I multiply anything by 1 in matrix forms, we multiply it by the identity matrix. So that's the equivalent of our 1. So this eigenvalue times 1 is the same as this term up here, just this bit here. There's no change. There's no change. Okay, those two things are equivalent. and my x1, x2 still exist, equal to 0. So just introducing that. Now if I go and do multiplication, each of the parts gets multiplied. And like algebra, if there's a 0, the term will disappear, and if it's a 1, it'll remain. And so we'll have this lambda and x1, x2. Now if I take the common factor, because there's a big algebraic minus there, what's common to both of these expressions? x1 and x2. So I can take the common factors out, and I can treat them like x1, x2. So that's bringing out my variable. So I put it on the right hand side, which is not the way you'd normally do it. So if there was something common in here, normally what you do is you'd pull it out the front. Okay, all I've done is put it out that side. Okay, for matrix form, because the side that you're on with matrices is quite important. Alright, so at this point here, we're nearly at the jumping point, but we're not quite there. So if we go ahead and do the subtraction of the matrices, each of the corresponding addresses get to subtract the equivalent corresponding address. So one corresponding address is lambda, so it will be 1 minus lambda from matrix subtraction. 6 will subtract 0, 5 will subtract 0, and 2 will subtract lambda. And because it's algebraic, we get to write it like this. So I'm going to draw a bit of a line in the sand here and write this as 1 minus lambda. 6 minus 0 is just 6. 5 and 2 minus lambda. So we've still got our x1, x2 pairing, and it's equal to 0. So this is the jump in point, and that may have happened to you when you did it in Calculus 1. Okay, I made that point last week, I think. I'm just going to click off here and have a look. Yeah, jump in. So we're jumping in here. Okay, so for our purposes, all of that matrix algebra and manipulation, at some universities that will be required. Okay, at some, and that's on your own. Here's the work, go do it. Right, and here some places jump you in here. So UTS has a bit of a habit of doing that with the non-mathematicians and the non-statisticians. They tend to, the engineers, scientists, teachers, etc., generally get the jump in. I think that's fairly reasonable to say that. So the next thing that we do is that we put together a determinant using this information. So we take the debt of this thing. So this is like the next step. Okay, so we effectively solve this. So if we do a 3-by, you can imagine if I were to do all the pre-work for this, there's those 6 or 7 steps prior to this step, right? And so what we're going to do here is we'll jump in and do the det for that one, but we're not going to do that right now because we're going to finish this one. But this is just a 2 by to keep it fairly simple for you. Now, what's the determinant? The determinant is the first address holder, this one. So 1 minus lambda multiplied with the address holder over here, 2 minus, so this is the times bit, okay? Subtract, and then we've got 5 times 6, and I'll put them in brackets just because we don't want to be lazy. Okay, and then we can expand all of those. So we just use FOIL. So FOIL is first, outside. So first is 2, outside is minus, inside is minus 2, and last is plus squared minus 30 equals 0. So we've got lambda squared minus 3 lambda minus 30 plus 2 is minus 28 equals to 0. Now this is important because it's called the characteristic equation. So we need to be able to do the determinant and generate this characteristic equation. So the solutions of the characteristic equation, as you can see, are quite simply quadratic. Okay, so there's a number of things that you can do to solve a quadratic. You can do sorry, I'll just fix that. So what are the methods? 2 numbers that add up. And multiply. Complete the square. Quadratic formula, which we've derived, which we know how to derive, and grouping in pairs, which I don't know if I did grouping in pairs with you guys. I don't know, but they're more helpful with non-monics. That's ones that have got a leading something. Alright, so we can visit those. Now again, if you see something there that, now I've hit those 3 pretty hard, but I don't know how much I've done in grouping in pairs with you, so that might be something you might say to me, oh, can you do those? But you've got to bring it to me, guys, alright? You've got to ask me, because otherwise I'll think you're on top of it, which is good if you are. Okay, so the first thing we want to do is just solve this. 2 numbers that add up and multiply. What are the roots of 28? Well, it does have roots. 28 and 1, and 4 sevens are 28, and 4 and 7 have a difference of 3. So it looks like we're going to have a pairing in linear form that looks something like this. So lambda squared tick, 4 times 7 is 28. One of them's got to be negative to give us this term. So it's in the negative, so the bigger one's got to be negative and that one's positive. So if we check that, lambda times lambda, lambda squared tick, minus 7 lambda. Actually, there's a learning opportunity here. Let me just quickly do this. Sorry, I'm going to move that down a little bit. Okay, so what did I say? 7, I put it up there, doesn't matter where you put it. So minus and a plus will give us that. So lambda times lambda is lambda squared tick. So I'm going to do it. Lambda, I'll tick above the line and put lambda squared. Sorry, I'm running around a bit, aren't I? So lambda squared, then we've got minus 7 lambda plus 4 lambda and minus 28. Now, grouping is 4 terms. So that's the version, that's the clue to grouping in pairs. So if you get a quadratic that's a bit iffy with a non-monic quadratic, you just pull apart the middle term into what you think might be suitable candidates, and then you can address it from there. But we'll do that another time if you want me to do that. If you're across it, that's fine. Now again, we haven't finished because we need to solve for lambda. So lambda is going to be what makes this 0. In other words, what makes this 0, which makes this true, and lambda must be -4. What makes this 0, that makes this true, because 0 times whatever will be 0, and it has to be 7. So students often don't get that bit too. Pulling that, you'll do a shortcut. If you do a shortcut at high school, it's going to be very hard for them. All right, now these are our eigenvalues. Wow, we got it. Okay, so we got our eigenvalues. So in the matrix algebra, in the AX equals lambda x, we've got this part. Okay, so remember this is a simplification of this process by finding out our eigenvectors. All right. And remember, they were unknowns. Okay, we had the transformation matrix. I didn't make the point at the time, but we had the transformation matrix, and these were unknowns. This is an unknown vector. Okay, so that's why these are a bit tricky, because in the other ones I've talked about, we've known the vector, and I did the example with the 2 and the 1 and the 1 and the 2. Okay, and I picked do you recall that? So I think we went like this, and that's 2, 1. And then we said we wanted it to be transformed, a reflection in y equals x, to 1, 2. And so we did our sum of products. So it was something like 0 row down column, tick, and row down column. So that's the A and the X. Okay, so that's our transform matrix. So what I would, that's the example that we go. Here we've got unknown. We're doing a transformation, but we've got an unknown. So this is why these get a bit tricky as well, because we start off with unknown vectors. Okay. All right, so what we do then is we take those vectors and we put them back into our system. So if we've got to find corresponding eigenvectors now, use, call it lambda 1 and lambda 2. Okay, so we start off with -7, or 7, and so we've got 1 minus lambda, 6, 5, 2 minus lambda, x1 and x2 are what we're seeking, is equal to 0, 0. Now we've expressed 0, 0 in vector form, so it's always going to be the case that we'll have zeros. Now, what can we say about any vectors, matrices, that are equal to 0? And so this might be a little bit of revision. So I don't know how well this will take, and I'll probably repeat it, so don't be alarmed if I just drop it now. But if I have 2 lines, okay, that's the cross, so there's unique solutions. Okay, if I have parallel lines. Parallel lines are no solutions. They never cross. Okay, they never cross. So that has no solutions. And the final group is where it appears as though it's one line. That is, they're coincident. Okay, so you've got the three sets of equations. You've got unique solutions, those solutions, and no solutions. Okay, now normally we would do that if I were fitting this in, but it's revision, remember. So this is the infinite solutions, and that's equal to 0. Whatever's going on over here, it's the one that's equal to 0, and notice we've got equal to 0. So when we do this, we will always get this class. Okay, so whenever we do eigenvectors and eigenvalues, it won't be this class of system, it'll be this class of system. Okay, and these are often characterized by this notion of what's called a free variable. Okay, and we'll look at that. Alright, so I might need to do that again a couple of times for that to go in. But remember, this is all assumed knowledge, so this is why I'm holding your hand and being careful with you, okay? I didn't want to hit you with the next section after the break and not have done this background. Okay, so what we've got to do is put it in. So we've got 1 minus, now it's a plus 7, so we can just go minus 7, 6, 5, 2, minus 7. Okay, and I'm actually going to be a bit cheeky, and I'm going to augment these. So I'm going to bring that in. I'm actually going to put a line down here and do it like that. So I'm going to treat it like that, and so I'll just then step to solutions. So in a way, I've augmented. And when you augment, you effectively disassemble the equation, looking like an equation. Okay, where's the equation gone? Well, we augmented it into this system. So I can just do it like that. So 1 minus 7 is minus 6. Now, frustratingly, 2 minus 7 is minus 5. So that's the system that I'm dealing with. Frustratingly, what happens in textbooks and even the notes, I've been pondering the idea of giving you some linear algebra notes, but I'm not going to. These are your linear algebra notes. Okay, is that all right with you? I gave you those resources on the Maths Study Centre website, and that's got the high school version of matrices in it. For our purposes, I think that's enough. Okay, I don't need to give you a university level linear algebra book. Has any one of you done linear algebra as part of your course? No? No, I'm not going to load.
So I did it as part of, because I did an undergrad in science and I did a course, but to be honest, I don't remember much.
Yeah, no, that's all right. No, I've just, as you can, what I'm trying to do is manage the volume of work, keeping in mind that you're working and what your backgrounds are. So I'm really trying to be careful for you.
Will this be covered in, the algebra subject that there's an algebra
Discrete
subject?
math? Is it called discrete math?
I think, well, I'm doing the Masters of Secondary Maths.
Yeah.
And I know there's 3 calculus and there's a statistics and there's an algebra subject. I think this is covered in the algebra.
It may well be.
Yeah.
It may well be. But I have to do it for what we're doing. So I didn't want to just... Anyway, by the time you get to that, you'll be an expert, right?
Yeah.
This is the whole point. If it works, it works. This is the beauty of maths. If it works, it works. It just does. So it wouldn't matter where it worked. All right, so we're going to do a few row operations now, purely for the purposes of our own convenience. So row 1 is going to become row 1 divided by minus 6. So I don't need to be too pedantic about that, because minus 6 divided by minus 6 will be 1. 6 divided by minus 6 will be negative 1. I didn't change row 2, but sometimes they do it at the same time. Okay, the next thing I can do is, just for the purpose of convenience, is to do the same kind of thing with row 2 and divide by, what do you reckon, 5? 5 will do. So this will be 1 minus 1, 0, 1 minus 1, 0. And so we get to this final point. Now what we start to do is row operations that give us 0. So we're going to target this guy. And the way that we would do that is we would say row 2 is going to become row 2 minus row 1. So this is a very simple example. So we've got 1 minus 1, 0. Didn't change anything there. And then we've got 1 minus 1 is 0. Minus 1 minus 1 minus minus 1. So that's a plus. Minus 1 plus 1 will give us a 0. And 0 minus 0 is 0. So when we get this one here, this is the algebra now, not matrix algebra, just algebra that means infinite solutions. And that fits with what we did up here. So here's our infinite solutions. So that's the geometric interpretation. Sorry, I just bumped my camera there. That's the geometric interpretation. Okay, but the algebraic interpretation is that we will get a row of zeros in the bottom row. So after we do all our row operations, a result will be that we will get 0, 0, 0. So that begs the question, what's the algebra of these other guys? So what we would get here in our matrix is 0, 0, 1. That doesn't make any sense. No solutions. So that's inconsistent. You can't have 2x1, you can't have 0x1 plus 0x1 equaling some value. That's got to be 0. So that's the no solutions one. And here, if you've got your matrix, there'll be something equal to something else. So there'll be, you'll reduce down to two numbers. So the algebra will look like this. It may well be zeros there. The algebra will look like that. So this is a big note. If you're going to do algebra, as you called it, that's a big note. So that's the algebraic interpretation in matrix form. That's the geometry. This is the algebraic interpretation. That's the geometry. This is the algebraic. So we've got our lines there, 0, 0, 0. So that's the algebraic interpretation that suits that geometry. They go together, okay, in their categories. It turns out with eigenvectors that we're always here. We're always here. Now the way it gets taught in some places is that they use a free variable or a parameter. So just use that. Invoke a free variable or a parameter. Often a parameter is assigned t, but we'll just use the free variable one for this time. So if these were x1, x2 columns and constant columns there, and constant happen to be 0, constant equals 0, then what I can assign, invoke the free variable, that is assign x2 equal to 0. For the parameter version, I would say x2 is equal to t, and my algebra answers would have a t in there. Okay, but in this case here, x2 is a free var. Sorry, x2 equals to a free variable. Sorry, I've got to get that right. x2 as a, not necessarily 0. Can be 0, but it's a free variable. So in that case there, if we go ahead and do a rebuild, so if we were to rebuild this one up here, what would that look like? That would look like, if I rebuild this, that would be x1 minus x2 is equal to 0. So if I were to put that over, x1 would be equal to x2. Okay, for this simple example, now this process that we're going through, once you get to this point where you get your row of zeros, this is a big moment, because the next bit is to work out the vectors. And so we've got to work out what values will make sense. So if I redo the x1, x2 variables, and look what we just said. We just said x1 is equal to x2. So an equivalent vector is x2, x2. Whoops. Okay. Now I can pretend that that's a result of a multiplication by some number, x2. So what would my vector be? 1, 1. Okay, so these steps here, look, I'm just going to put dots and dashes because this is the difficulty. You thought that stuff up there was difficult. This is the difficult one. Okay. Therefore, vector v is equal to 1, 1. So that's our eigenvector with its associated eigenvalue. Let's try that out, shall we? Let's try that out. Transformation matrix. There's our transformation matrix. Now that's the original form. We should be able to multiply that by our eigenvector. And what are we looking for? Okay, so row down column. Row down column is 1 times 1 plus 6 times 1, which is 7. Row down column, 5 times 1 plus 2 times 1 is 7. Okay, nearly there. 7 can be brought out like this. Okay, so those steps, those bits at the back, that line, it's all very well to assign this, tick, 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 we got there. This next bit is what students really, really struggle with. Okay, but we have found the eigenvector. And the eigenvector that gets transformed by this is 1, 1, and it turns out that it gets stretched to 7, 7. So the geometric interpretation of running the vector via this transformation matrix is that we go from 1, 1 to 7, 7. In other words, it got stretched. And it still remains on the, what do we call that? Does anyone recall? Doesn't matter, it's not that important. I gave it to you last week. The span. It still remains on the span. Thank you. So it is typical of the eigenvector result. Now that's not that hard, is it? Now if we can do that in 3D, we're going very well. Now the other thing is, I'm just going to quickly do the 4, all right? And before I do the 4, I'm just going to pause the video, and because what that does is it stops it. So stop that one.